Hi, everybody. This is the exam review. So this is for the content involving chapters 12, 13, 14, and 15, starting with z-tests, then single sample t-test, then paired samples t-test, then independent samples t-test, then power is chapter 15. So here's how this is going to work. I'm going to give you a question. There's actually 20 questions that we're going to go through. If you get it right, then you'll go on to the next question. If you get it wrong, you'll go to a description of me explaining the correct answer to the question. And if it's a calculation question, I will then calculate it using different forms. I will calculate on Excel, and I'll do it two different ways on Excel. I'll do it just doing the normal math, just like from scratch. And then if it's possible, I'll do it using the data analysis tool on Excel. And then I will also do it on RStudio. So I'll do it in three different ways, depending on the test, obviously, the ways that are available to you. Okay, let's go ahead and begin with the first question. All right, well, for this question, we're looking at, I want to know if being in a relationship makes people play more Pokemon Go. Which statistic would I run in order to compare the people in a relationship to those who are single? All right, now, normally you would think, hey, this is an independent samples t-test, right? Because people who are in a relationship are different than the ones who are single. And that is true, they are different. But the problem is that the dependent variable is playing Pokemon Go. And if you look at the data, you see that playing Pokemon Go is either yes or no. That is not a continuous variable. It is a categorical variable. So we actually do not have any test that can compare anything having a categorical variable in and out of a relationship compared to a categorical variable, which is whether or not you play Pokemon Go. So the answer to this one is none of the above. All right. Question number 2. All the participants in my sample are from California. All right, so everybody's from California, right? The whole sample is from California. Good. I think the Californians are more likely to play Pokemon Go than the rest of the population. What test will I use? Well, same problem. In this particular case, we do not have an indication of what the population is, right? And the outcome variable here is a categorical variable. So we could look at, the whole population compared to things in a binomial, but I didn't give you binomial as an indication, right? So we'll get to binomials later on, but in this particular case, the z-test, single sample t-test, paired sample t-test, none of those can do that because the dependent variable for a z-test or any of the t-tests, the dependent variable must be continuous. You have to be able to calculate a mean. Otherwise, you can't do any of them, and that's kind of the point. Number 3. I think the Californians spend more money on Valentine's Day than the rest of the population. Now, what test would I use? For this one, I could use a z-test or a single sample t-test, depending on what information I have. So if I have the mean of the population, then I could use either one. If I have the mean of the population and the standard deviation of the population, then I can use a z-test. You use a z-test to compare one sample to the population when you know the population's mean and standard deviation. Use a single sample t-test when you compare one sample's mean to the population's mean when you only know the population's mean. Use the sample's standard deviation for the single sample t-test. Number 3, I think the Californians spend more money on Valentine's Day than the rest of the population. Oh, that's the one we just did. Sorry. Question 4. Question 4. I think the Californians spend more money on Valentine's Day than the population. The mean amount that people spend on Valentine's Day is $100. That means the population's mean. What is the value of the statistic that I should run? Okay, now for this, we need to calculate a single sample t-test. Now, I didn't tell you what test to run, and I'm not going to tell you what test to run. You need to know. In this particular case, all I have is the population's mean, which is $100. And so I need to look at the data from the beginning to figure this out. So let's go ahead and go to the data. I have it ready for me in Excel right here. And the question was, since all of these people are from California, I'm looking at the whole sample, all of them from California. So that means I need to look at this. How much money you spent on Valentine's Day? That's expenses on Valentine's Day. Okay? I was already given the population's mean. So let me put that over here. That's mu. So mu equals $100. All right? I do not have the population standard deviation yet. I don't have it. So I've got to use what I do have, and that is the sample's standard deviation. So let's get the mean and the standard deviation for the sample. So the mean is going to be the average of all 20 of these scores. And the standard deviation is calculated the same way we always do our standard deviations. We can go through and do the deviations and then square them. In fact, if you want to, you can do that right now. Let's go ahead and do it. Let's do this as the deviations. All right, and then this is going to be the deviations squared. And let's move mu out of the way so it's not in our way. Let's move it over here. So deviations are going to be x minus x bar, which is this right here, right? So we've done this a million times. All right. Those are the deviations. And then these are going to be the deviations squared. The sum of those will be the sum of squares. The variance is going to be the sum of squares divided by n minus 1. And there's 20 people here, so 20 people is our n. So divided by 19. And then standard deviation is going to be the square root of the variance. All right? If you don't want to go through that whole process, there's an easier way to do it. The standard deviation, Excel can do the standard deviation by going equal stdev.s, because the standard deviation of the sample, not the population. So this one right here, stdev.s. And double click on that, and then only include the original scores. Don't include that mean, original scores, and you get 40.602. What? It's the same thing. Look, there's the same. All right. Now, since we're running a single sample t-test, we need x bar, the mean, minus mu, divided by, but it's not the standard deviation by itself. It's the standard deviation divided by the square root of n. Remember, whenever we're doing a z-test or a t-test for the single sample, we got to divide it by the standard deviation divided by the square root of n. So let's go ahead and get the square root of n. So that's going to be the square root of n is 20, right? So the square root of 20, 4.47. So S sub x bar, which is the standard deviation of the means, right, is going to be the standard deviation divided by the square root of n. So most time when people are making a mistake, they forget to divide the standard deviation by the square root of n. Then t is going to be, x bar minus the mu, and then I have that in parentheses to make sure that there's no mistaking, no, dividing things when they're not supposed to, divided by the standard deviation of the means, which is S sub x bar. When we do that, we get negative 4.31216. So the answer when we round it to 2 decimal places is negative 4.31. And remember, this is a t-test, not a z-test, because we were only given mu, which is the standard, which is the population's mean. We were not given the standard deviation of the population. So the answer is negative 4.312. Okay, so the question was, should we reject or fail to reject the null hypothesis based off the statistic that we just calculated? The statistic that we just calculated is that right there, t equals negative 4.31. Now remember, this is a t, a single sample t-test that we just did. It is not a z-test or a binomial. So that means we need to look at the t table. Now, degrees of freedom for a single sample t is n minus 1. N is 20. We have 20 people in this sample, right? N minus 1 is 19. So our degrees of freedom is going to be 19. So let's go ahead and look at the t table. This is the z table, so do not look at that one. That's not the one we want. We want the t table. So let's go ahead and get rid of these old markings that I have on here, and so we can look at what we need to look at. So in this particular case, alpha is always 0.05 for this exam, and it's always going to be a two-tailed test. Therefore, we will always be right in this column right here. That is definitely where we are going to be. We just told you that degrees of freedom for the single sample t-test is n minus 1. N was 20, so therefore our degrees of freedom are 19. That means that the critical value of t is 2.093. Now, since it's a two-tailed test, we also have negative 2.093. So that means negative 2.093 is right there. The statistic that we calculated was a negative 4. What was it? I can't remember. It is negative 4.312, right? Negative 4.31. So if it's negative 4.31, that means that it is, let's put it right over, well, it's way over here, okay? And that's a lot more extreme than the critical value of 2.093. So you reject the null hypothesis. But wait a minute, we got a little bit of a problem. Let's take a look at our original hypothesis and make sure that it's going in the direction that we expect. So in this particular question, I think Californians spend more money on Valentine's Day than the population. In this particular case, we find that they are spending significantly less money than the population, not more, right? And they're spending more money, they're spending significantly less money. So technically I should reject the null hypothesis, that's correct, but it's going in the wrong direction. Californians are spending less money on Valentine's Day, not more money on Valentine's Day. How do I know they're spending less money? We'll take a look. The mean amount was 60.85, and the average of the population is $100. So I know that's significantly different, but going the opposite way of what I originally thought. Okay, number 6. I think that Californians spend more money on Valentine's Day than the population. The mean amount the population spend on Valentine's Day is $100. The standard deviation for the population is $60. What's the value of the statistic I should run? Now, in this particular case, it's no longer a single sample t-test because now I'm comparing my sample, all of my sample, to the population. The population's average is $100, but the standard deviation of the population is $60. That means I am now running a z-test, So the way I do this is very similar to the single sample t-test. Let's go ahead and run it using my Excel right here. So mu was $100 still, but now sigma, which is the standard deviation of the population, is $60. So instead of using the standard deviation from the sample, I'm now using the standard deviation from the population. Basically, it's a very similar idea. So now I need to get sigma sub X bar. That means I need to get the standard deviation of the population, which is sigma, divided by the square root of n, divided by the square root of 20, which is 13.41641. Then I need to calculate z-test. My z obtained. The z-test is x bar, let me put it in parentheses so I get it right, x bar minus mu, so the mean of my sample minus the mean of the population, divided by sigma sub x bar, which is the standard deviation of the population divided by the square root of n. When I do that, I get negative 2.918704. So correct statistic is negative 2.9187807, or to round it up, negative 2.92. So question number 7. Based on the value calculated for the last question, should I reject or fail to reject the null hypothesis? Now, in this particular case, we are looking at a z distribution, not a t distribution. So we are going to look not at this table. So let's erase all that, by the way. Let's get rid of it. We're not looking at this one anymore. We're now looking at the normal distribution. That's the z table right here, the one we love so much because it's a z test. Now, in this particular case, we do not look up the critical value like we normally do, because the smaller portion, that area right there, that's the probability that we would need to do. So we're looking for a z of the critical value, but we're looking for 0.05 in the smaller portion, except it's a two-tailed test. So we need to split that 0.05 into two tails. That means we need to look up 0.025. So when we look up 0.025, we find it right, let me circle it for you, 0.025 right there. That is a z of 1.96. So the critical value for a two-tailed test for z is 1.96 or negative 1.96. But what about the degrees of freedom, you say? Well, there's no degrees of freedom. When we're talking about the normal distribution, there's no degrees of freedom. It's normal. That you don't have to have degrees of freedom. No degrees of freedom. It is what it is. In fact, for a two-tailed test in a z, it is always going to be 1.96 when alpha equals 0.05. It's always, 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 always. I don't care what your n is. I don't care what anything else is. If you remember correctly, our calculated statistic was negative 2.92, negative 2.92. So when we look at this, negative 2.92 is more extreme than 1.96, or in this particular case, a negative 1.96, because it's two-tailed, negative 1.96. More extreme than that, therefore, we reject the null. But remember, wait a minute, we are rejecting the null, but it's going in the opposite direction of what we originally thought, right? Californians are spending significantly less on Valentine's Day than the population. It is more extreme, negative, more extreme than a negative 1.96. So reject the null, but it's going the wrong way. Okay. Next. Number 8. I think that people spend more money on Valentine's Day than on Halloween. What test should I run? All right. So for this particular case, we need to run a paired samples t-test. A paired samples t-test. The way that we're going to do this, we're going to do it two separate ways. I'm going to do it on Excel, and then I'm going to do it on RStudio. So paired samples t-test is going to go something like this. Let's go ahead and pull up this one right here. So remember, what I'm looking for is the difference between expenses in Halloween and expenses on Valentine's Day. So let me just go and expand those so you can see it. Expenses Halloween, expenses on Valentine's Day, right? Okay, good. Now, we've already looked up the deviation squared and all that stuff for Valentine's Day, but that is not what we are looking for. It's not what we're looking for in this particular case. Instead, what we're looking for is the difference between expenses on Valentine's Day and expenses on Halloween. So let's go ahead and find the difference. Now I'm going to go ahead and move our mu and sigma and z-test, get that out of the way so that we can talk about other stuff. Let's put those back over here because I won't think we need them. The difference is going to be the difference between Valentine's Day and Halloween, meaning Valentine's Day minus Halloween for each person. For each person. When I do that, these are all the data that I get. Okay. Now I need D bar, and D bar is the average of the difference. It's this average. It's not the means. That's not what we're looking for. We're looking for D bar. So we need to get the mean, which is equals average of all of these. All right, 3.7. That's the difference, the mean difference. And then we need the standard deviation. And that is going to be the standard deviation of a sample, stdev.s, for all the original difference scores. Okay, and then we need S sub D bar, which is S sub D bar is going to be the standard deviation divided by the square root of n. Remember, square root of n, we've done that a million times. 13.13, that means t is going to be the mean of the differences, d bar, minus 0, because that would be the predicted difference if everything, if the null hypothesis was true. So we don't even have to do that one. So d bar divided by s sub d bar, which is standard deviation divided by the square root of n, and you get 0.281674. There's another way to do this. That is, if you have already in your Excel gone to Files, gone to Options, gone to Add-ins, this is a little bit different in a Mac, I understand that. Add-ins, come on add-ins. Excel, come with me. There we go. And you manage your add-ins. If you have Analysis Tool Pack checked, then you have this special option under Data, Data Analysis. And under Data Analysis, you have a t-test paired for 2 samples for means. When you click on that, you can then tell them which ones you want, and you use the original data for this. So I want to compare Valentine's Day to Halloween. Now I've included the labels here, and I've told them that right there. So when I push OK, this is what I get. And you'll see that this is the same information that we just calculated before, except I didn't have to go through all the other math. The mean money for Valentine's Day was $60.85. For Halloween, it was $57.15. These are the variances for each, right? If you want, this is the Pearson's correlation. You don't need that. Here's the degrees of freedom, because degrees of freedom for a paired samples t-test is n minus 1. And here is the t-statistic, 0.28167. Now let's see if that's similar to what we, oh look, it's the same, 0.28167. Look right there, isn't that great? Hey, now, if I want to do the same thing, I can also do it in RStudio. So in this particular case, I've already downloaded all the information. So I went to Import Database, and I chose the Excel document, and now I need to attach, because I hadn't attached it yet. You only have to do this once at the very beginning. I need to attach calculations for exam. There it is. And just to make sure you got the spelling right, I always love to click on this instead of actually trying to type out the whole thing so you don't get any underscores or anything wrong. Okay, now I need to do a paired samples t-test. So the paired samples t-test is going to be, it's going to be t.test, and then I include the two variables that I want. I want expenses for Valentine's Day, comma, expenses for Halloween, comma, paired equals, and then true, put it in all caps. T-test, expenses for Valentine's Day, comma, expenses for Halloween, paired equals true. And when I click on that, boom, here is what I'm gonna get. Let's move this up so you can see. T equals 0.28167. Let's see if that's the same as what we calculated before. T equals 0.2816. Oh, we are so good. Look at that. So great. So the answer to this question is 0.28167. You can find it here. You can find it here. Or you can find it here. That's the correct value. All right, next question. Number 9. Based on the value calculated for the last question, should you reject or fail to reject the null hypothesis? And the answer is, let's take a look. There's 3 different ways we can look at it. Here's the first. Let's go back to the original that we got. 0.28167. If we look at the T table, which is not this table, let's go ahead and erase those. This is the Z table. How do I know? Because it says the normal distribution Z. I need a T table. Here it is. Nope, that's the correlation. There's the T table. T distribution. All right, now remember, everything for this exam, alpha equals 0.05 for a two-tailed test. We're always doing that one. Now, in a paired samples t-test, degrees of freedom is n minus 1. There's 20 people, n is 20, n minus 1 is 19. Therefore, the critical value is 2.093. The value that we calculated, if you recall, is 0.28. 0.28 is not anywhere close to 2.08, whatever it is, right? So let's just remind me what that is. It is 0.208 or something like that, right? We're not anywhere close to that, so we have to fail to reject the null. Here's the other way you find it. In Excel, if you use the data analysis to calculate it, which I did right here, then look, here's the T critical. Let me pull this over so you can see what it says. T critical for a one-tailed test, we want a two-tailed test. Here's the T critical for 2.093, not 8, 2.093. And here's the p-value of this statistic, 0.28167. This right here is a lot bigger than 0.05. We fail to reject. The other way to find it is in RStudio right here. Here's the p-value of the statistic 0.28167. That is a lot bigger than 0.05, so we fail to reject. Okay, so now we need to look on question 10. I think that people who are in a relationship spend more money on Valentine's Day than people who are not in a relationship. What test should I run? And the answer is you should run an independent samples t-test, an independent samples t-test. Why? Because people who are in a relationship are independent, separate people from the ones who are not in a relationship. So if I think that people who are in a relationship spend more money on Valentine's Day than people who are not in a relationship, I should run an independent samples t-test, and here's how I do it. There are lots of different ways we can do it. So let's go ahead and do it the original old-fashioned way by calculating the means and the sum of squares and all that stuff. So I want to compare people who are single, those who are relationship, and how much money they spend on Valentine's Day. Now in Excel, you have to put these into different groups. So I'm going to help myself out on this one, just so, because otherwise it's kind of annoying. I'm actually going to sort these. I'm going to sort all of mine to be separated into singles versus in a relationship. So the way I'm going to do that is I'm going to go to data and I'm going to push on sort, and I want to sort by their relationship status, which is B, and my data has headers, so that's relationship status. There it is. Good. Okay, and when I do that, as long as I have everything, all of the data highlighted from the original stuff, then here's what I get. And remember, we're looking for how much money you spent on Valentine's Day. So here's all the people who are in a relationship. All right. And here are their expenses on Valentine's Day. Okay. Control C. This is going to be in a relationship, huh? So let me write that down. In a relationship. And these are all their data. Oh, I didn't copy correctly, evidently. Copy and paste. There we go. There's all their data. Here is single. Okay. And here's their expenses on Valentine's Day. There we go. So let's go ahead and move over, and we're going to use those data now. Notice how we have the same number of people. So N is going to be the same. N of the first group is 10. How do I know? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. And then N for this group is also going to be 10. Then let's go ahead and get the mean equals average of these people right here, these 10 people. And the mean sub 2 is going to be right there. Great. The standard deviation. The standard deviation for each group, this is going to equal standard deviation of a sample. Maybe right there. This is the sample that I want. And then here is the standard deviation for the other group. Which is this right there. Okay, now here's a reminder of what we're trying to do when we're looking at an independent samples t-test. Now in this case, the n is equal, so we can use the equal n's formula. Let's go ahead and pull that up just so that we remind ourselves how to do it. It is chapter 14. Okay, here we go. So let's go ahead and look for independent samples t-tests. And we are looking, whoop, come back to me. That's the long formula. So we need to find, that's paired samples. And here is independent samples, assuming equal variances for n equals each other. X bar minus 1, or X bar sub 1, minus X bar sub 2, so the means of each group minus each other, divided by the standard deviation, sorry, this is not the standard deviation, it's the variance, right? Because it's S squared. The variance of the first group divided by its n plus the variance of the first group divided by its n, and you take the square of that whole thing. All right, so that's what we're going to be doing. That's what we're going to be doing. So let's go and put this over in the corner, and so we can kind of see it while we do this. So instead of just the standard deviation, now we need the variance. And that is just the standard deviation squared. Right? So here's the variance. Okay, there we go. When we did this, then we need to find the variance of the first group, so the variance of the people in a relationship divided by n, so divided by 10. So that's going to be variance divided by n is going to be this divided by 10, right? And then variance divided by n for the other group is going to be this divided by 10. And we're going to add those up. The sum of those is going to be sum of this and that right there. 193.73. Then we need to get the square root of that. Square root of this, 13.91. And so then we get our t when we go x bar sub 1 minus x bar sub 2, 87.2 minus 34.5, divided by the square root of the variances divided by n. They add them up, get the square root. That's what you get, and it is 3.7862. Now, if you don't want to go through all that math, here's an easier way to do it. You go to data. You go to data analysis. You go, instead of the paired sample, you go to the two samples assuming equal variance. So two samples is the same as independent samples, and you assume equal variances. That's why we're going to put var equal equals true in the RStudio thing in just a minute. But you assume equal variance. Do not touch the unequal variances one. We never use it in this particular class. When I click on that, it's going to ask which ones are you talking about. I'm going to say, well, I want the first group to be here. You know what? I actually want it to be in relationship to because I got a label on it. And then I want the second group to be the single people. Don't include my n on that one. Good. And I push OK. And here's what I get. Here's the mean, the variances, the observations, meaning the n for each group. That's going to give me the pooled variance. We'll talk about that later. And then here's the t-statistics, 3.786232. Let's see if that's the same. 3.786232. We did it. It's the same. Good job. Here's the way to do it in RStudio. In RStudio, for an independent samples t-test, you do t.test, and then you put the dependent variable first. Now, in this particular case, the dependent variable is how much money you spent on Valentine's Day. Expenses on Valentine's Day. Well, what do you want to split it by? The tilde means split it by whether or not you're in the relationship, which is relationship status. And then you need to put comma var dot equals true. You need to tell them that the variances are assumed to be equal. Otherwise, it'll give you a Welch's t-test, which is not the same thing. When you do that, here's what you get. 3.7862. Look at that. 3.7862. It's the same as 3.7862, which is the same as 3.7862, getting all the same piece of information. Okay. The next question is, based on the value calculated for the last question, should you reject or fail to reject the null hypothesis? And the answer is, I have an independent samples t-test, and that independent samples t-test value is the original one right there, 3.79 is what we're going to round it to, 3.79. 3.79. Now, what about the degrees of freedom? Degrees of freedom are n sub 1 plus n sub 2 minus 2. It's everything minus 2. So there's 10 in the first group, that's n sub 1. 10 in the second group, that's n sub 2. You add those together, you get 20. Minus 2, you get 18. So it's 18. When you look at the table, let's erase this because now, even though we're still in 0.5, those are not, 19 is not our degrees of freedom anymore. Independent samples t-test is a little different. The degrees of freedom for an independent samples t-test is 18. That means that the critical value is 2.101. We calculated a t-statistic of, if you recall, 3.78. That's more extreme than a 2.101. That means we can reject the null hypothesis. The other way you can do this, if you did it on Excel, is if you did it over here, 3.78 right there, the p-value for a two-tailed test right there is 0.001. That's a lot lower than 0.05. Here's the critical value if you want to do it the other way, right? Saying 2.10, right? Which is the same. as the critical value that we found right here, 2.101. Remember, same stuff. So we know that we are going to reject the null hypothesis because this is less than 0.05 and this is more extreme than that critical value. The way you do it in RStudio is even easier. You look right there, there's the p-value. It is less than 0.05, and if you ever want to know, the mean of the people in a relationship is 87, the mean of the group that are single is 34. Check those means every time to make sure they're going the right direction, just like we did with the other ones. Okay. Now, question number 12. I think that people who play Pokemon Go spend more time outside than do people who do not play Pokemon Go. What test should I run? And the answer is you should run an independent samples t-test, and here is how we are going to do it. This one, excuse me, I happen to know that our n's are going to be different on this one. So back to the original data. Here we go. Back to the original data. We want to now look at people who play Pokemon Go compared to those who do not. So I'm actually going to sort these data. I'm going to sort the original data by going to data, sort, and I'm going to sort it instead by Pokemon Go, yes or no. And that's going to put all the no's on top and the yeses on the bottom right there. And I am trying to figure out whether or not the people who do play Pokemon Go spend more time outside than the ones who don't. So let's go ahead and put that over here. So here is yes, and here is no. I better make room. Here's yes, and there's no. So the no's spend this much time, and the yeses spend this much time. All right, so let's scroll over there because those are the ones that we need now. In fact, let me just move these over a little bit more so that I don't get in the way of my other data. Let's put them right here so they're totally out of the way. All right, so we know in this particular case that n for this group, let me just make that a small n is going to be 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those, so n equals 8 for the people who do play Pokemon Go. However, for the ones who don't play Pokemon Go, n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There's 12 of those, so there's 12. So let's go ahead and get the mean. The mean for this group, the standard deviation, and the variance, which equals the standard deviation squared. Good. Let's just make sure I check this. I didn't do a problem. Yeah, that's good. Looking good. All right, let's do the same thing over here. So now we need the mean. The mean is the average of those on the standard deviation. Whoops. Standard deviation of these. Good, and the variance is going to be this squared. Good. Okay, now let's look at the formulas just to remind you how this is a little bit different because now our n's are a little bit different. So let's go back to that PowerPoint slide of our, that's not the right one. There we go. So let's go ahead and look here. Whoop, there we go. So here's what we want. We want to get t, I'll put it over on the other side so it's easier to see for now. X bar minus x bar sub 1 minus x bar sub 2 divided by the pooled variance divided by n sub 1 plus the pooled variance divided by n sub 2 all over, and this is how we get the pooled variance. N sub 1 minus 1 times the variance of the first group, n sub 2 minus 1 times the variance of the second group, n sub 1 plus n sub 2 minus 2. Okay, so now we need to use the pooled variance to get what we need. So let's go ahead and move this over here so we can use it later on if we want to. And let's go ahead and do, whoops, what did I lose the formulas so that you can see them? Come back. There we go. That's it right there. Okay, so what we need to do is get the pooled variance first. So the pooled variance has got to be n sub 1 minus 1. So n sub 1 is going to be 8, right? So there's 8 people who play Pokemon Go. Minus 1 is 7. So for this first group, I'm going to get this to get to the pooled. We need to get n sub 1, which is 7. So this is going to be 7 times the variance. All right. This, on the other hand, is going to be 12 minus 1, which is 11. So n sub 2 is 12. There's 12 people who do not play Pokemon Go. So 12 of those minus 1 is 11 times the variance. So this is going to be 11 times the variance right there. Got it. Good. 34.25. Then when we add those two together, I'll put that sum right here. The sum of those is the sum of this one plus, whoops, I did that wrong. Sorry. It equals this plus, come on, I messed it up. Equals this plus that. All right, so that's the sum. That's the top of the numerator of the pooled variance right there. Divided by the degrees of freedom. Degrees of freedom is n sub 1 plus n sub 2 minus 2, which they add up 20, minus 2 is 18. And then the pooled variance. Pooled variance is this divided by the degrees of freedom right there, 3.0625. That's what it is. So now we need to get the denominator for the t statistic. So that's going to be the pooled variance. So this is going to be the pooled variance. Let's go ahead and do both of them. Pooled variance divided by n, which is n sub 1, which is 8, right? Plus the pooled variance. I'll put the parentheses just to make it look better. Plus, sorry, pooled variance divided by n sub 2, which is 12. So this is going to be that, and then we get the square root equals the square root of this 0.79, 7799 essentially. That's going to be the denominator. So then t is going to be x bar sub 1 minus x bar sub 2 divided by that big denominator that we just created right there, 3.599. Now, if you don't want to go through all of that, go to the data analysis tool, and we do t-test, 2 samples assuming equal variances. You do assume equal variances, even though the n's are different, they're still equal variances. So what you're doing is, now I'm going to go back over here. The first group is people who play Pokemon Go compared to the ones who do not. And when I click on this button, now I get this. Let's check and see if we got the same thing for everything. The mean for the first group, 6.125. That's correct. The mean for the second group is 3.25. Also correct. The pooled variance, 3.0625. Let's check it. Let's check it. Let's see that pooled variance, 3.0625. We did it. Good job, us. Then our T statistic is 3.59932, and that is the same as our T statistic, 3.5932. When you do this in RStudio, you do it just like you did the other one with the ends equal. It's exactly the same. T.test. And in this particular case, I want to know hours outside separated by Pokemon Go. And then var.equal equals true. And when I do that, here's what I get. Now, here's something. This gave us a -1. The reason why it gave us a negative is because it doesn't matter which way it goes, frankly. It doesn't matter. That's why they give you the means down here, right? So these are the no's, and these are the yeses. Is it positive or negative? It doesn't matter, and it won't matter to you either. But the correct statistic is negative or positive 3.993 or 3.60. I'll accept either one. Positive or negative doesn't matter. Okay, next question. Based on the value calculated for the last question, should you reject or fail to reject the null hypothesis? There's several ways we do this. Let's go back. Here is the statistic that we calculated, 3.9932. That's a 3.60. The degrees of freedom are n sub 1 plus n sub 2 minus 2. That is 8 plus 12, which is 20, minus 2 is 18. So when we do this, we go to the table. And when we went to the table, 18, the critical value is still 2.101, and our statistic that we just calculated was more extreme than that because we got a 3.59. That's more extreme than a 2.101, so we're going to reject the null. Here's the other way we know. We look at this, and it says, hey, there was our p-critical for a two-tailed test, 2.100, it rounds up to 2.101. Here's our t, that's more extreme. The p-value of the t statistic is 0.0025. That's less than 0.05. So we reject the null. In RStudio, it is right here. The p-value is 0.00205. That is less than 0.05. We reject the null hypothesis. Okay. Next. What is the pooled variance for the last question? Well, lucky for us, we had to calculate it. So we already did it the hard way. When we added all these up, we used, let's show you the, we used the pooled variance, which is n sub 1 minus 1 times the variance of the first group plus n sub 2 minus 2 times the variance of the second group divided by the degrees of freedom. When we did all that, we got this, 3.0625. Now, if you don't want to do that, you can just look here on the Excel table, and when you do that, you see that the pooled variance is right there. They always tell you what the pooled variance is. Now, in RStudio, they do not show you the pooled variance. So they're not going to give it to you. You're either going to have to calculate it yourself or use Excel to do it, but you're not going to get it here. Now, there are ways, I know there are ways to get it, but I'm not going to show you what to do. I want you to know what the pooled variance is, be able to calculate it. So that's what it is. It is easiest to find using Excel. It's 3.0625 or 3.06. Question 15. I think that psychology majors are more likely to volunteer their time than other students. I plan to measure 14 psychology majors to see if they do or do not volunteer. What's the power for this scenario? Okay, now the reason why I did not use data that we already had is because you're supposed to use power when you're planning a test, not after you've already done it. So power is the probability that we can say that psychology majors volunteer more when they actually do. So if we say that psychology majors volunteer more, then we are rejecting the null hypothesis. The null hypothesis is that they don't volunteer more. If we say that they do volunteer more, we're rejecting the null. When they actually do, that means that the null is false. So rejecting the null when the null is false, that's power. The probability of being able to reject the null when the null is false is power. Question number 16. I think the psychology majors are more likely to volunteer their time than other students. I plan to measure 14 psychology majors to see if they do or do not volunteer. If 50% of the normal population volunteers, how many psychology majors would have to volunteer for me to reject the null hypothesis? Now, in this particular case, the dependent variable is whether or not you volunteer. That is a binomial. That is a binomial. So we are looking at the binomial table. I'm going to go ahead and pull up the binomial for you. Here it is. Here's one. Let me erase a bunch of stuff that I was working on before. And so we can look at this together and not be distracted. Now in this particular case, let me make sure that I've got all the information right. We are talking about 14 psychology majors, right? So N is going to be 14. The normal population volunteers 50% of the time. That means the null hypothesis is that 50% would volunteer. Okay, that's the null hypothesis. So that means that when we're looking at the chart, we are looking for N equals 14. Let me go ahead and highlight some of this. N equals 14, right? And the null hypothesis, I'll put the null in red because we don't, well, I'll put it in orange. It's not totally, whoops, that's not the right one. Erase what I just did, sorry. It's 0.5. The null hypothesis is 0.5. And when we want to reject or fail to reject, then we're looking at the null. Okay, now, for everything in this test, it is a two-tailed test with alpha equals 0.05. That means that the two tails, so here's a tail, 0. Here's another tail, 14. So starting at the two ends of that distribution, I've got those p-values have to add up to 0.05, and then I'm going to stop rejecting values. So if 0 people out of 14 volunteer, the probability of that happening is 0.00006, okay? Plus 0.00006. All right. When you add that together, you get 0.0012. Okay? That's less than 0.05. So let's go to the next value, 1 and 13. So for 1, it's 0.000854 plus 0.000854. You add those together, that is also less than 0.05. So we could reject the null with 0, 1, 13, or 14. Let's check 2 and 12. 2 is 0.005554 plus the probability of 12, which is 0.005554. When you add those up with the other ones that we already got, we are still less than 0.05. We are at 0.0 something, 1 something, right? Now, here's the issue. When we add the probability of 3 and the probability of 11, it's going to push us over 0.05 because we have to add, they have to be the cumulative. It has to be all of those values. We're looking at both tails. It's got to be all the values in both of the tails. So all of these together. And we know that if we add those up, they're going to be more than 0.05. Therefore, the only values that we would reject, right? So if we end up doing 14, we have 14 students in our study, and we think this, then they're all psychology majors, and we think the psychology majors study more than other college students, then we would have to get 0, 1, 2, 12, 13, or 14 psychology students to volunteer in order for us to reject the null hypothesis. All right. 17, I think that psychology majors are more likely to volunteer their time than other students. I plan to measure 14 psychology majors, see if they do or do not volunteer. 50% of the normal population volunteers, and I think that 80% of psychology majors volunteer. Calculate the power of my study. So we already calculated that we will only be able to reject the null hypothesis when 0, 1, 2, 12, 13, or 14 people volunteer. Now, when we are correct, if we are correct, then that means 80% of psychology majors will volunteer. And so all we are doing is calculating the probabilities of the values that we can reject the null hypothesis. So 0, 1, and 2, 12, 13, and 14. And now we're doing it instead of the null hypothesis column, now we're doing it for our hypothesis. So we are adding up the probability of 0, 1, 2, 12, 13, and 14. We're adding up all of those values. That's what we're doing. I'm going to actually do that right now. I'll even do it here on my other calculator just to make sure we have exactly the correct amount. You only have to round to 2 decimal places, so it's not going to be that big of a deal when you do it. But let's go ahead and go from the bottom all the way to the top if you need to. I suggest you actually go from the top to the bottom because those are bigger numbers. Let's see what we can do. All right, so let's go to the top, from the top to the bottom. So the probability of 14 people, 14 people in this case, volunteering is 0.04398. 0.04398 plus the probability of 13 people, which is 0.153932 plus 0.250139 plus the probability of 2 people, which is 0.000000239 plus 0.0000000. My calculator's not even going to let me do this one. Right? These are basically zeros. I can't even put these on my calculator. They're so small. When you add up all those probabilities, you get 0.25. Almost exactly 0.25, right? So this plus this plus this plus this plus this plus this, that is power. Why those 6? Because those are the only values that we can reject the null, right? So the answer is 0.25. Power is 0.25 for that test. Okay. I think that bunnies have longer ears than other animals. I know that the average ear length for all animals is 5 inches. I have 20 rabbits with an average ear length of 12 inches and a standard deviation of 6 inches. What is my estimated effect size? So this, in case you didn't realize it, is a single sample t-test. It's a single sample t-test that we have to work on because we're comparing our sample, bunnies, to the population of all other animals. And we have the mean for all other animals, so that's mu, the mean for the population. Then we have the mean for our sample, which is 12, and the standard deviation for our sample, which is 6. And then we also have our n, which is 20. So in order to do this, let's go ahead and show you the formula one more time so that we can get all the information that we need. I'm going to stick this on the side so I can see my values on this. Let's go ahead. Is this what I want? Nope, that's my independent samples. So let's pull up my other one, which is right power. Okay, so here's what we're going to get for power. Come back, power. All right. Power for the single sample t-test is going to be, there it is right there. It's going to be, sorry, I keep sticking the wrong thing. All right. It's going to be D hat. Now that means the estimated effect size. So D is the effect size. The estimated effect size that we're going to get is x bar minus mu divided by standard deviation. So we want to get x bar. Now if you remember, x bar is going to be 12, right? Our samples standard deviation is 12. Or not, it's the mean is 12. 12 minus mu, which is 5. So 12 minus 5 is going to give us 7. Okay, 7 divided by the standard deviation of 6. So 7 divided by equals 1.17. Okay, so our estimated effect size, 1.17. Question number 19. I think the bunnies have longer ears than all other animals. I know, blah, blah, blah. This is the same as the last one. What is my delta? Well, we calculated our effect size, estimated effect size, to be 1.17. Delta is the standard, it's the, the effect size times the square root of n. So 1.17 is our effect size. N, in this particular case, how many do we have? 20 rabbits. So the square root of n is 20 square root 4.47 times our delta. So the square root of n is 4.47213, blah, 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 times our delta, which is 1.1666, repeating. We're going to get 5.2174. So 5.22. 5.22 is going to be our delta. Okay, the last question then, what is power for this test? The estimated power, we go to our table for power, which is right here. This is the table for power. Alpha equals 0.05. This is a two-tailed test, same as always. But now we have an estimated delta of 5.71. The highest that we have possible is 5. That means that we're off the charts, and the estimated power is going to be 0.99 because it's it's basically 1.0, but the closest is 0.99. Okay, great. This is how you do. Let's go back to this. This is how you're going to do a single sample t-test using RStudio. So go t.test. Now, if you remember in the actual question that we wanted, the question was, I think that Californians spend more money, let me make this big, more money on Valentine's Day than the population. The mean that the population spends is $100. What statistic should I run? And the answer is a single sample t-test. And here is the answer to this one using RStudio. It is t-test. So this is t.test of expense on Valentine's Day, comma, and this is what I want to compare it to. Mu equals 100. And that's all. That's all you need. It's enough right there. So the mean amount that we got in our group is $60.85. The actual p-value of this is right there, and the t-value is negative 4.3122. When you compare that to the calculations that we made, we calculated it being over here. We calculated our single sample t